In this appendix subchapter of chapter 6, Electrochemical Impedance Spectra or spectroscopy, I'd like to show you how to use the software to fit the experimental impedance spectra with an equivalent circuit model. In this presentation, I'd like to use the software, the name of which is GView, which is provided by the Scrivener Associate. So let me introduce how to download those freeware from the Scrivener website. So just type Scrivener. Then in the very first link, Scrivener Associates homepage is here. So please click it. And then go to the software section, and you could find several software. Among them, please check the GView. And you could download from this tab. And no, it's not the link. So you could download the GView from here. So click updated March 5th 2020. Then you could download those exe files. Let me assume that you have downloaded the GView software and then installed it in your desktop or laptop computer. Maybe you cannot install the software in your the cell phone. Okay, then actually I have installed the GView. So here is the very first screen of the GView. You could find two windows. The first windows is about the Nyquist plot. The x-axis is G prime, which is the real part of impedance. And on the y-axis, you could find G2 prime, which is the imaginary part of impedance. In this case, you could easily see that the minus signs in front of the values, because usually we are using minus y-axis for the electrochemical impedance spectra. Let's go to the second window, and this is the amplitude of impedance versus frequency, and also phase angle versus frequency. Those two things are called Bode diagram, B-O-D-E, Bode diagrams. Okay, right now we have empty complex domains or Nyquist plots and Bode plots because we don't have any data here. So at the very first place, I'd like to simulate some impedance spectra by using equivalent circuit models. So let's go to the menu, and you could find some RC circuit. This is the window for the equivalent circuit models. So just click it, and then you have a new window. So in this empty space, I'd like to draw an equivalent circuit model. I will draw some spectra having two semicircles with one Wahlberg impedance, like in the lithium-ion battery case. So let me try it. So just right-click on the point of the line, and then you can find some menu. Then let's go to the new series after Then let me choose the resistor as an element type, and then element name is made by yourself. In this case, I'd like to type like RS because I will make the solution resistance. So okay, then we have one resistance here, and then also you have another thing on the below window. That is the line for the information about the solution resistance. You will write down the value here. Anyway, after setting up the equivalent circuit model, then we will go to the values in the bottom window. Then again, right click on the end of the line. No, not on the end of the line. The right click on the element. Then let's go to the new and series after. Then let me change the element type to the capacitor. Actually, not the capacitor. We should go to the constant phase element rather than resistor. Like that, CPE. I have said, please use the CPE instead of the capacitance, because we should think about some non-ideality of the capacitance. Then here I can say CPE1 because this is about the first circle. No. Like SEI. I'm simulating the lithium-ion battery examples. So instead of CP, just write down SEI. But even if I have said this is the capacitance of SEI, but this is actually CP. This is just name. Then okay. And then right click, then new and parallel after, or before parallel after. Then I will add another resistance for making the semicircle, so RSEI. Okay, that's it. And let's go to the second semicircle about the interface between the graphite and SEI layer. So when you click this dot, then you could add some element after this circle. So please like that, new series after, then another capacitor, but instead of capacitor, please use the CPE, and this is, let me say, CDL, double layer capacitor. Okay, and then you could set up the CDL after the parallel circuit, and then click the CDL and then new parallel after, then resistance, and this resistance is charge transfer resistance at the interface between graphite and SEI layer. So like that. And we need to have one more things, the lithium ion transport or diffusion within the graphite. Then I'll select the RCT in the second parallel circuit. Then new after series, then I will add the Warburg. But here's the Warburg, right? But you don't need to use the Warburg impedance. Please use the constant phase element. Constant phase element would cover the capacitance and also Warburg impedance. CPE. And let me say Warburg. Okay, that's it. This is the equivalent circuit model for the anode material, lithium intercalation into anode graphite or lithium-ion batteries. Then let me input some values. Just follow me. Rs is 1 and SEI capacitance is 10 to the minus 5. And actually CP has two parameters. The first one is about the capacitance and the other thing is the exponent. Actually in the previous chapter slide I have used N instead of P, but N is equal to P. P means power. So let me say this is 0.8. You know, when P equal to 1, I could say this is the capacitor. However, typically we cannot obtain ideal capacitance. So far away from 1, it means non-ideality is increased. I mean, again, when P is going away from 1, it means your capacitance is going to more non-ideality. So here 0.8. Usually P value would be between 0.5 and 1.0. More practically, P value is around 0.9. Then let's go to the second semicircle R charge transfer, in this case 15 ohm, and the other thing is CDL value, double layer formation capacitance 0.002 and P value is 0.8. Okay. Okay, let me change the P value about the first circle. Let me here 1.0. I mean this CP is the ideal capacitance. This one. Then RS is equal to 1 and RSE, sorry, let me say this is 3 and 15. Anything is okay. But here's an example I have defined already. Then the other thing is Warburg impedance. Actually, the Warburg impedance, I mean the exponent of Warburg impedance should be 0.5. And let me assume that its capacitance value is 1. That's it. We are ready for simulation. There are no freedom for each parameter, and this button is saying run simulation with frequency range. Then let me check what kind of ranges are set up there. The option is here. Edit in the model menu. Edit fit parameters. So right now we are on the simulation mode and frequency range is fixed between 0.001 1 millihertz to 1 million hertz. That's enough. Then okay. Then click the run simulation. Okay, that's it. Then I kill this window. I cannot see the two semicircle with one 45 degree line. Why? Because we did not scale, automatic scaling. So please, A indicates all. So please click this one. Then you can find some semicircles. And Warburg line. So two semicircles with Warburg, and then let me select those data. Right now, no active data, but click and then fit result. Then you can find some data points on the impedance spectra. So please click the arrow button. Left arrow, right arrow, anything is okay. Then, could you see it? This square with red boundary is moving like that, right and left. So you could find the values of this point. So in this case, frequency 12882, and the real part of the impedance like that, and imaginary part of impedance like that. So we could move this one, and you can find another green square. So please tap the spacebar. Then red boundary moves from this one and this one. Right now you could move this green square. So left, please click the left arrow buttons or right arrow buttons, something like that. By using this green square, you could select some range of your impedance data, and also you could read the values of the point on which the green square are there. So again spacebar, and then I moved the green square on the left side and right side. Okay, right now we have a data. Then I'd like to save this data to the data file. So again, click the equivalent circuit model windows, and then here is the save data button. Save data button, and then you should find some location. I'd like to go to the desktop background, and then new folder, and let me say example, EIS. Then let me rename this file. What is the file name? Let me say lithium ion batteries, and click the save. Okay, and then okay, right now you have saved the simulated data. Then okay, from now on, even if from now on the data is loaded from the file you just have saved, is considered as the experimental data. So let me upload the files. Please click this G button, and then please go to the folder you have made. In my case, on the desktop I have EIS folder. Then I can find lithium ion battery G file. Then click this file, and then click the arrow from the left to the right. Then okay, so right now the lib.z file is loaded, and then let me try to find it here. Actually the same thing. This data is the simulated data you have just made. However, forget the simulation. Let me assume that this is the experimental data I have just obtained from my frequency analyzer. Okay, then let me try to fit this experimental data with the equivalent circuit models. Again, let's go back to the equivalent circuit model window. And then of course you have just made it, and then here's the value. Actually this is the answer. I mean, solution resistance 1 ohm, the SEI resistance is about 3 ohm or something like that. But forget it. We don't have no information about that. And then let me try to change the mode from the simulation. Oops. No. Mode from the simulation to the feeding mode. So edit feed parameters, and right now we are on the simulation, but let me move to feeding section, and let me check the all points. Then okay, right now we are ready to feed the experimental data with this equivalent circuit model. Also, forget the right answer. Okay, just remove some values. 0, 0, 0, 0, 0, 0, 0, 0. And then freedom is fixed. It means we cannot change the value. So click it, and free plus means this value should be positive. One more click. The question, it means this value could be positive and also negative, but positive is enough. Okay, that's it. And then we will fit this experimental data with using this equivalent circuit model. Actually, complex non-linear least square feeding is used for the feeding. I have said non-linear. So we need to have a very good guess as the initial guess. How can we expect the values as the initial guess? Actually, you have learned about that. RS, you could read this value, right? Right now, the red boundary is on this green square. So you couldn't move it. And then let me try to read the x-axis at the very high frequencies here. So right now, the frequency is 1 million hertz, and the x value is about 1.0006. So your first initial guess for the solution resistance is 1, right? Right. The true value is 1, but anyway. And let's go to the first semicircle. What is the diameter? Let me check it. So this is 1 ohm, and then let me move the green circle. So this value is about 4. Maybe if you extend this semicircle part, then maybe 5. Anything is okay. This is just initial guess, but the exact answer will be provided by this software via complex nonlinear square fitting. So let me say 5. Is it the real value? I'm not sure. No. This is this is 4, and this is about 5, and the diameter is 5 minus 1, 4. It should be 4. Okay. Then the capacitance. Let me just how about the non-ideality or the exponent? Always please assume the power is 1. I mean, I'm thinking about the ideal capacitance. So 1 is enough. This is just the initial guess. And then let me go to, what am I doing? Sorry. This is for the SEI resistance 4 from the diameter from the first circle, and the CP value the power of the CP is assumed to be 1 ideal capacitance. And then you have learned about how to guess the value of T in the CPE or Warburg, right? So by using So how can you expect the value about the capacitance value? Let's go to the frequency at the top of the semicircle, around here. Then what is the frequency? About the 600, or let me say 6,000 hertz. And then this 6,000 hertz is correlated with the RC constant. So you know the value about the resistance, and then the top frequency you have obtained, so you could calculate the capacitance value. Okay, I have just calculated the value of capacitance like that. So from the top frequency, which is the about 5600 hertz here, and 2 pi f is equal to 1 over RC time constant, and R value is estimated at 4 here. So then by calculation, C is estimated around 10 to the minus 4 farad. Actually, the true value is 10 to the minus 5. However, 10 to the minus 4 is enough as the initial guess. So let me say 10 to the minus 4. Okay, then how about the other thing? How about the second semicircle? Let me read the diameter. About this is 5 and this is the 20, so 15 is enough. I'll charge transfer is 15. Actually, this is the true value, but however, by your eyes you could expect around 5 and 20, so 15. How about the the capacitance value? Anyway, the exponent of CPE is assumed to be just 1, always 1 as the initial guess. And how about the capacitance value? By using these equations, you could expect the value. In my calculation, it is around the, let me check it, 10 to the minus 3. 10 to the minus 3. And how about Warburg impedance? Also, you have learned about how to guess the value of T of the Warburg impedance. Anyway, the exponent of the Warburg is assumed to be 0.5, sometimes 0.49 or 0.51, but in this case I have assumed that our Warburg is ideal behavior. And the T, capacitance value, or some parameter value about the Warburg. So in this impedance spectroscopy chapters, you have learned about how to guess the value of the T value, T parameter of the Warburg. So use this method. Then I have guessed the T value is around the 1. Then we are ready. We have all initial values and we are ready. After just clicking this button, right now you could read run fitting. Then you could find the values are changed inside of this box. Okay, so the initial value is very important thing. If you have a very bad initial value, you cannot find the good answer about this non-linear least square fitting. But I believe we have good initial guess and then learn fitting. It takes some time. Then finally, we obtain the final value. RS actually true value was 1 but 0.99999. Great. And the capacitance value, my initial guess was 10 to the minus 4, but right now we are going to the true value about 10 to the minus 5, actually 1.0001 e minus 5. And how about the exponent of this capacitance? 0.9999959, so almost ideal capacitance. RS is 3 exact value. How about the other thing? T 0.002, the exact value. How about P, the exponent of the CP is 0.80001, which is a little bit deviate from the true value of 0.8. RCT true value. How about Warburg? Our initial guess was 1, but it is changed into 0.99997, and exponent of the Warburg should be 0.5, but actually it is not the exact value. So right now 0.4999. So by using this method, you could fit the experimental data with your own equivalent circuit models. Anyway, after you investigating the experimental data, you should make your own electrochemical equivalent circuit models. That is on your own way. You should on your own way for making the equivalent circuit model. That's it for fitting the experimental data by using equivalent circuit model.